Find the release for stage 1 for the optimal reservoir operations. In this problem, a reservoir begins at stage 1 with a volume of 4 units of water. At the beginning of stages 2 through 5, the volume in the reservoir must be between or equal to 2 and 8 units of water. In this problem, there are 4 stages, so the beginning volume at stage 5 is the same as the final volume of stage 4, after the inflow and release. The inflow for all 4 stages is given, and the release during each stage can be 0, 2, 4, or 6. Associated with each release is a benefit, where there is a larger benefit associated with larger releases. The state dynamics equation relates the volume of water in the reservoir from one stage to the next, where V equals the storage volume of water in the reservoir, Q equals the volume of water released from the reservoir, and I equals the volume of inflow. We can represent the possible reservoir storage volumes for all stages using a box diagram, where the different states of the reservoir I1 through I5 are labeled sequentially, and the numbers in each box 2, 4, 6, and 8 represent the possible storage volumes for each state I. From this diagram, we can label the 4 stages as the space between state I and state I plus 1. During the stage is where the inflow, I, increases the volume of the reservoir, and the release, Q, decreases the volume of water in the reservoir. If we focus in on stage 4 and return to the state dynamics equation and set I equal to 4, then the storage in the reservoir at the end of stage 4, V5, equals the previous storage, V4, minus the stage 4 release plus the stage 4 inflow. From the problem statement, we know the inflow during stage 4 equals 2. Also recall that the reservoir can release 0, 2, 4, or 6 units of water at each stage. Next, we'll trace out all the possible paths from stage 4. For example, if the storage volume in the reservoir at the beginning of stage 4 equals 2, then if we release 0 units of water, the final storage volume will equal 4 units of water. If we release 2 units of water, the final storage volume will equal 2 units of water. Since the minimum storage volume in the reservoir equals 2, we cannot release 4 or 6 units of water. We'll next evaluate whether or not we should release 0 units of water or 2 units of water to maximize the benefits, assuming we start at V4 equals 2. Before we do, we'll rearrange our box diagram such that the state variable, which is the storage volume, resides in the top half of the box, and the optimal objective function value, capital F, in the bottom half of the box. Since there is no benefits associated with the state variable, we'll assign a 0 benefit to the final state variables. Returning to the benefits table, for stage 4, we realize there is 0 benefit for releasing 0 units of water, and a 1.9 benefit for releasing 2 units of water. Since our objective is to maximize the benefits, the optimal operating policy depends on whichever release will maximize F4, for a storage volume of 2. After writing out the equation for the 2 possible releases and substituting in the benefits for stage 4 and the future benefits at state 5, the maximum benefit equals 1.9 when 2 units of water are released from the reservoir. Next, we'll repeat this process, but assume that there are 4 units of water in the reservoir at the beginning of stage 4. We also know the inflow for stage 4 equals 2. Therefore, if we decide to release 0 units of water, the reservoir will have 6 units of water at the end of the stage. Releasing 2 units of water will result in 4 units of water at the end of the stage, and releasing 4 units of water will result in 2 units of water at the end of the stage. As before, 6 units of water cannot be released due to the minimum volume constraint. We'll find the optimal release by finding the maximum benefits when the volume equals 4 units at the beginning of stage 4. After writing out the equation and substituting in the benefits from stage 4 as well as the future benefits, the maximum benefit equals 3.9 when 4 units of water are released. For V4 equal to 6, the reservoir can release 0, 2, 4, or 6 units of water. After plugging in the benefit values for releasing water from the reservoir and for the future benefit values, the optimal objective function value is 4.8, which corresponds to the reservoir releasing 6 units of water. Lastly, when the reservoir starts with 8 units of water, at least 2 units of water need to be released in order to not violate the state variable constraints. Releases can also be made for 4 units of water and 6 units of water. When evaluating the objective function value, we'll expand the equation out, substitute in the appropriate terms, and determine the optimal value equals 4.8 when the volume at the beginning of stage 4 equals 8, which corresponds to releasing 6 units of water. At this point, we've established the optimal operating rules for releases for stage 4, based on the volume of water in the reservoir at the beginning of stage 4. We also know the maximum benefit associated with these optimal releases. Next, we'll move on to stage 3. In this stage, we'll determine the optimal releases using the same objective function as we did with stage 4, by evaluating each initial storage volume one at a time. The differences with this stage will be the inflow is different, the benefits associated with each release are different, and the future optimal objective function values are also different. For more space, we'll shift the box diagram to the right and temporarily remove the final state I equals 5. Then we'll look at the state dynamics equation to know which releases, Q3, are feasible, based on the volume in the reservoir at the beginning of stage 3, V3. Knowing the inflow is 0 and knowing the storage, V4, is constrained to be either 2, 4, 6, or 8 units of water. For V3 equal to 2, the only possible release for Q3 is 0, because the minimum storage volume in the reservoir at the end of stage 3 is constrained to be at least 2 units of water. Similarly, we can determine the possible releases for initial volumes of 4 units of water, 6 units of water, and 8 units of water. As an example calculation for stage 3, we'll determine the optimal release, Q3, for 8 units of water at the beginning of the stage. After writing out the objective function and expanding its 4 equations, then recalling the benefits associated with releasing 0, 2, 4, and 6 units of water for stage 3, plugging in those values into our objective function, then plugging in the future optimal objective function values we calculated for stage 4, the maximum benefit of state 3 with 8 units of water equals 8, which corresponds to releasing 4 units of water in stage 3. After evaluating the other 3 starting reservoir volumes for Stage 3, we can determine the optimal releases as well as the maximum benefits. Looking at the entire box diagram, we've already determined the optimal releases for Stages 4 and 3, and we're left to analyze Stages 2 and 1. Stage 2 is solved the same way as Stage 3. Stage 1 is also solved the same way, except the initial state variable is constrained to equal 4 units of water. Next, we'll look at just Stage 1 and write out the state dynamics equation. After substituting in 4 for our initial storage volume and 4 for the inflow, we learn that releasing 0 units of water will result in a storage volume V2 equal to 8. Releasing 2 units of water will result in V2 equal to 6 units of water. And releasing 4 and 6 units of water will result in storage volumes of 4 and 2 at the end of Stage 1, respectively. Since the question asks to find the release in Stage 1, then we can determine the solution by revisiting the objective function for this stage. Then write out the 4 terms, recall the benefits associated with each release quantity, plug in those benefits, as well as the future optimal objective function values, which equals the maximum of 13, 13.3, 13.4, and 12.1, which is 13.4. This maximum benefit of 13.4 is associated with a Stage 1 release of 4 units of water. When reviewing the possible solutions, the answer is C.